Hi, it's my pleasure to present our work on explaining online reinforcement learning decisions for self-adaptive systems. My name is Andreas Metzger, and this is joint work with Felix Feit and Klaus Pohl. So in the following, I'll motivate our work, which is then followed by the introduction and details on the explanation approach we call XRL-DYNE. And I will also show a brief insight into our validation, showing the usefulness of the approach applied to a concrete self-adaptive systems exemplar. And at the end, we'll have a critical discussion and outlook on future work. So let me start with some foundations on what we understand with online reinforcement learning for self-adaptive systems. In simple terms, it's an emerging approach that allows us to address design time uncertainty so that we don't know everything about the context, the future situation in which a self-adaptive system may have to operate. And online reinforcement learning means we can leverage information that we will only have available at runtime once these design time uncertainties are resolved during live system execution. Learning in general is being the, let's say, increasingly explored approach for building self-adaptive systems. And actually, in fact, since 2019, the use of learning even dominates other strategies such as rule-based approaches for building self-adaptive systems. To explain you a little bit more what online reinforcement learning in the combination with adaptive systems mean, we created a, if you wish, a reference model we published as part of our previous work, which combines the MAPE-K reference model of self-adaptive systems with a simple reference model for reinforcement learning. So I guess the MAPE-K loop is known to the audience, the typical adaptive system control loop, if you wish, including monitoring, analyze, plan, execute, which is based on a common knowledge base. This here is the typical reference model for reinforcement learning you'll find in most of the textbooks. So you have an agent which interacts with an environment, and the idea is that in a given environment state, the agent can execute an action. Executing this action leads to the next state as prime, and the agent receives a reward for entering this next state. And the idea of reinforcement learning is to define the rewards in such a way that they express the learning goal, and over time the agent learns how to optimally behave in this environment. This entails three elements: the action selection, so what action to perform in a given state; a policy which prescribes the action selection strategy; and obviously a policy update which improves this policy over time based on the rewards received. And if we combine these things now in online reinforcement learning for self-adaptive systems, you will see, I can also use the laser pointer, that the policy represents the knowledge of a self-adaptive system, which gives the kind of how the adaptive system should behave in a certain situation. And action selection is a combination of the analyze and plan phases, meaning is there a need to act or adapt, and in this setting, what kind of adaptation would be the best, right? So I think this is a very nice model to understand how we can integrate these both paradigms and follow up from there what we'll present in the rest of this presentation. What we do in particular in our work is we use deep reinforcement learning, which means that the policy is represented as a deep neural network. This has certain benefits you'll see in a minute. In particular, we use value-based deep reinforcement learning, which means that the policy is represented as a so-called action value function, giving you the expected reward in a given state for executing an action. Why did we choose deep learning? Obviously, you saw some of the very nice examples what deep learning can do, and this is just one thing I played around with at the weekend. So it's the Midjourney AI, one of these image generator AIs, and I just told them, please generate a yellow Labrador, actually our yellow Labrador, in the style of, you probably could guess, Monet, Kandinsky, and Mark. Okay. So this shows the power of these deep learning algorithms. In our concrete setting, the benefit is that using deep learning, we can handle continuous state and actions. So you can have a very large input space made up of continuous states and actions. And the other benefit is that you can generalize over unseen neighboring states. So you don't have to explore all these states, which basically is also impossible if they're continuous, in order to learn. The biggest downside is that deep learning obviously appears as a black box. If you have a deep neural network, it has many parameters. And just looking at the parameters as an engineer, you will not really understand what this black box is doing, which is in contrast to traditional reinforcement learning approaches, which are based on things like a tabular action value function, like Q-learning does, where you really have for each of the states and each of the actions, you have the expected reward put down in a tabular fashion. And what you see here is the cliff walk example. So the aim of the reinforcement learning agent is to go from start to goal and not fall into the cliff. And what you very nicely see is that these red areas here are really large negative rewards. This means if the agent is in this state and would go down, it would fall into the cliff. Whereas at the very end, if the agent takes down, he would reach the goal, right? So this is very nice mapping of the problem to the learned policy, which you completely lose in deep learning. So this means if we use deep learning, despite the benefits, we have limited trustworthiness in whether the agent is doing what it should. And even more importantly, in the setting we're here in software engineering, it's very difficult to debug whether we have prescribed the reward function in such a way that the actual learning goal is achieved. And you will see later in our experiments, the reward function is not really easy to define, so it's a potential source for human error. This means we need explainable reinforcement learning if we want to apply deep learning in practice. Obviously, we're not the first dealing with this problem, and you see here a lot of existing state-of-the-art and initial ideas how you do so. For the sake of time, I'm skipping this, so you have the slides here as reference, and also, of course, you have the paper where you can see things in more detail. On the right-hand side, you have examples for typical explanations created to illustrate what these techniques are capable of doing. So this leads me to our approach, which in simple terms is combining and augmenting existing reinforcement learning explanation techniques from AI research, in particular the so-called reward decomposition approach and the interestingness elements approach. And this is why we call our approach decomposed interestingness elements or DINEs. Why did we choose these two? They have very nice characteristics that complement each other and, let's say, resolve each other's downsides. Reward decomposition means you don't define a single monolithic reward function, but you split it into smaller sub-reward functions. And looking at the smaller sub-reward functions, you can then better understand what is the learning or action selection strategy of the agent. The interesting elements are there to see along the whole course of when the online reinforcement learning runs at operation time. What are the relevant moments of interaction where the agent may be not so certain what he's doing and where you should look at as an engineer whether there's a problem in how the agent behaves. So the reward decomposition has the obvious benefit that it helps understanding the decision-making of the agent in the presence of multiple competing goals. And this is a situation you typically have also in adaptive systems. And the nice thing, it also provides contrastive examples. So what would have happened if another decision would have been chosen? The problem is you don't know which of these explanations are relevant. So in the worst case, after each time step or after each learning episode, you would get an explanation, and many of them may not be really interesting. They don't contain interesting information. So you would have to select manually the relevant ones, which of course adds cognitive overhead. The benefit of the interesting elements is exactly addressing this gap to select the relevant interactions, but with the downside that the explanations are not really decomposed and understanding why the agent behaves like that. It just tells you you should look at this point of interaction because it may be interesting. And obviously, this is where the reward decomposition comes in. So this is the basic idea of XRL DINE. What this means in more detail is that we can now define different types of these DINEs depending on what kind of explanations we're interested in. And we have defined 3 of these DINEs based on the state of the art, but also modifying them for the specific problem of deep learning and also of the self-adaptive system. So the first DINE we have defined is the so-called important interaction, which tells you whether the agent takes a decision with a high certainty, or whether the agent may not be so sure what he may be doing. And you can see this here in the dashboard, which is part of our prototypical implementation, that in the case here, you see exactly there's one action which has been decided upon, and all the sub-agent, sub-reward functions have agreed on it. Whereas here you have a situation where there may be 3 different actions taken by the different sub-agents. So you could say, well, there's some kind of uncertainty or even conflict of decisions. How we compute this, lots of details here. I suggest you look at the paper to understand this better, because we're running out of time otherwise. The important thing here is we can define a so-called threshold row, which allows you to say how strong should the inequality of the individual decisions be for being shown on the dashboard. So this is a way to control the amount of information shown, addressing the cognitive complexity of the engineers. And we'll come back to that in the experiments. The second, what we have here is the reward channel extremum, which tells you along the course of learning, is there any minimum or maximum in the reward functions? Because this may be an interesting point when you have the change in these rewards that something interesting has happened. And so you want to may look at this in a little bit more detail. Yeah. And the third we have is the so-called reward channel dominance. For each of these points of interaction, you can say what's the influence of a sub-agent on each possible action. For example, here you can see for the add server action, either in absolute or relative terms, how strong was the vote, in a sense, of the sub-agent on choosing this action. In this case, the sub-agent, which was responsible for user satisfaction, dominated the choice over the revenue sub-agent, and the agent responsible for running costs didn't have any meaning here at all, if you wish. Again, I'm skipping this for sake of time. Validation. So what we did is 2 things. We first created a proof of concept implementation with a concrete deep learning algorithm, the double deep Q networks algorithm with experience replay presented by Hasselt et al. At AAAI. We use this because it allows to approximate the environment model using supervised learning by using the replay memory of this algorithm. And we need this approximation of the environment model to create one of the dynes. I skipped this for sake of time. And in order to make it compatible also with other environments, we may deploy our adaptive system in. We use the OpenAI GIM interface to connect both the reinforcement learning agent and the adaptive system exemplar. As a self-adaptive system exemplar, we chose SWIM, which is one of the SEAMS exemplars presented in 2018. It's a self-adaptive multi-tier web application where you have a client, a web, and a data tier, and you can adapt different elements of this web application. And you see which of them by now going through the reinforcement learning problem formulation. The action space has basically 3 different actions. You can add web servers, you can remove web servers, or you can change the dimmer value, which means that the number of recommendations created by the front end, by the client, can be tuned in order not to create too much load on the infrastructure. The state space is made up of the request arrival rate from users, the average throughput and response time of the web servers. And this leads us to a decomposed reward function, which contains 3 different sub-functions. The first is we want to optimize user satisfaction, which depends on how good is the response time and throughput of the web application. We want to increase revenue, which depends on how many recommendations we show the user and maybe convince him to buy more stuff on our platform. And of course, the costs are dependent on the number of servers running. And the result is shown here. You saw some of the elements of this already in the previous slides. It's a live dashboard. You can visit it via this link. And then you can really see over time how things behave. You can hover with the mouse over different areas here. For example, you could see the reward channel dominance for some of these interesting parts of the interaction. So as you can see, this would help the developer to get a high-level understanding of the RL's behavior and decision-making. For example, looking at the minimum maximum points, looking at the uncertain points. And if you're interested, you can drill down into more details with these reward channel dominance dynes. The second element we evaluated was the cognitive load, and we didn't do a user study, but we said, well, somehow the cognitive load may relate to the number of dynes shown to developers and that have to be understood by developers. And as you saw, there are certain parameters in the actual dyne which allow you to tune the number of dynes, the threshold here for the important interactions, which shows you how you can really reduce the number of interactions shown, and even can do it in a live setting, increase and decrease in the running system. And the same is for the reward channel extrema, where you can tune them up and down, which means depending on what you want to do, coarse-grained observation with very important interactions or in-depth debugging, you can really tune these things as you wish. Okay, let's critically discuss the limitations at the end. There may be certain situations where XLDane creates difficult to understand explanations. One reason may be that the reward function was decomposed incorrectly or non-optimally, and then of course the explanations look a little strange. And the other is that because of the environment dynamics, effects of adaptations are delayed, and thus the explanation you get are not really synced with actually what happens in the environment. Second limitations is we didn't look at explanations for collaborative adaptive systems. So if you use XLDine in a collaborative setting, you may get misleading explanations because we don't consider the behavior of the collaborative system. And this is a really technical, challenging limitation we did for value-based reinforcement learning. But the interesting alternative is policy-based reinforcement learning, which doesn't use a value function at all. And the benefit of this is you don't need to account for exploitation trade-off, and this can really nicely handle non-stationarity. But because you don't have a value function and no access to this Q of SA function, how to compute the dynes is currently open. Okay. Quickly looking at future work, and a nice framework to do so is look at the key requirements that were identified towards explanation in the social sciences literature. Tim Miller had a really great paper on that. First requirement is explanation should be contrastive, explaining you why P happened instead of Q. And of course, this is what we do in Dyne with the reward channel dominance, where you can see basically why not another decision has been taken. Explanation should be selective. You don't need to have all the information, but you want to have the important ones, exactly what we aim to do with the Dynes. Ideally, explanations are causal. So it's not necessarily that the most likely explanation is the best. And one idea for future work, because this is currently not done in Dyne, is check whether the agent relies on spurious correlations and thus maybe not considering causality. And the last very interesting point is that explanations should be social, because transfer of knowledge is part of a conversation. And one idea we have here is to use chatbots for explainable AI. So instead of giving you this simple one-shot explanation, here, for example, of a supervised prediction model, the training will be delayed and you explain why. You may enter into a conversation with a chatbot where you can get back and forth, ask questions, get a reply, and so step by step better understand the explanation. And with that, and a little over time, I thank you very much for your attention, point you to some further reading, and thank our sponsors. Thank you very much.